Hi there. My name's Jenny Fothergill. I'm a PhD candidate in the Material Science and Engineering Department at Boise State University. And today I'm going to tell you about a new tool I've developed called GIXStapose, which helps to validate molecular simulation data by interactively connecting the calculated diffraction pattern with its real space structure. In my lab, we use molecular simulation techniques, including molecular dynamics, to predict the self-assembly for a range of chemical systems, from the active layer of an organic photovoltaic to catalytic surfaces, nanoparticles, epoxies, and thermosets. Shown here on the left is an equilibrated snapshot from one of our OPV polymer simulations, and on the right is a real OPV device. So how can we validate that what we observe in simulation is consistent with experimental observations? One way we can validate our simulation results is using simulated diffraction. Grazing incidence X-ray scattering, or GIXS, is a technique commonly used to analyze the periodic features in thin films. Our lab previously developed a tool called diffractometer, which can read in a simulation snapshot and calculate its diffraction pattern by running the particle coordinates and periodic boundaries through a sequence of matrix transformations. If you'd like to learn more about the math behind diffractometer, I recommend this paper shown in the upper right. In the lower left is an example of diffractometer in action. Shown are two simulation snapshots, their diffraction patterns simulated with diffractometer, and good agreement with the experimental GIXS patterns of the real systems they aim to model. A limitation of diffractometer was that by default it would calculate the scattering patterns of the snapshot from 13 different views, including a face-on view, an edge-on view, a corner-on view, and then 10 other rotations to get ample description of the system. However, when looking at these simulated diffraction patterns, it was not always immediately obvious what view of the real space structure correlated with what diffraction pattern, and additional work had to be done to get that information back. For example, in order to make the above figure, the simulation data would have to be opened in a program like VMD and manually rotated and measured to look for these periodic features that most likely correspond to these bright diffraction peaks. And this reliance on manual rotating and measuring and looking for these features does not lend itself to a true simulation workflow. When I say true, what I'm referring to is an acronym coined by Peter Cummings in a lecture given at the 2019 Thermodynamics Conference. It stands for transparent, reproducible, usable by others, and extensible. And it's a principle that I really believe in my field. Because in the field of molecular simulation, it should be easy to reproduce the results of a paper. I should be able to download input files, load up the software stack, and press go on a workflow script and get the same output. But any computational scientist can attest that this is not the case. Manual editing of text files, command line interfaces, and differing versions of software can make reproducing computational work something of a nightmare. And when it isn't even common practice to report what version of a force field you're using, there's a lot of work to be done. And so we can use the principles of true, and we can use open source software, unit tests, continuous integration, and scriptable workflows and documentation and examples to help to make our workflows better. So we have aimed to keep true principles in mind when addressing the limitations of diffractometer, namely connecting of the views of the real space structure with their simulated diffraction pattern, and making it easier to diffract from any arbitrary angle. And the result is the GIXStapose library. The code can be found at the GitHub address at the top of the screen. And the name GIXStapose is a portmanteau of GIXS, grazing incident X-ray scattering, and juxtapose, because it juxtaposes the GIXS pattern with its real space structure. The library is designed to be used in two ways. First, as an interactive GUI. Here you can see it in action with one of our OPV polymer morphologies. And it's also designed to be used as part of a scriptable workflow. Although this is a GUI that is navigated with the mouse, all the camera information is visible to the user. So if they wanted to recreate this view outside of the GUI, it's easy to do because the code that generates the camera view can be printed to the terminal by selecting Print Camera in the menu bar. Under the hood, GIXStapose takes advantage of many open source packages, including the high-quality rendering of the Fresnel ray tracer, the ability to read in multiple chemical file formats of mBuild, and currently, GIXStapose is implemented as a diffraction module in the Freud analysis library. Also included in the GIXStapose repository is a Jupyter Notebook example of how to add GIXStapose to any scriptable workflow. A Jupyter Notebook allows us to display images and human-readable text along with executable code. This helps us to communicate the purpose of our code and make it more usable by others. So, what exactly was involved in the making of GIXStapose? GIXStapose ties together two codes, Fresnel, which is a high-quality ray tracer with a convenient Python API that can render a scene that's specified by its geometry, and diffractometer, which is a series of matrix transformations implemented in NumPy that just needs a set of coordinates and its periodic boundary. But neither Fresnel nor diffractometer is designed to work with a chemical input file by default. So I used mBuild, a chemical structure builder in the Molecular Simulation and Design Framework, or MOSDEF for short, which already knows how to read in most chemical file formats and then convert them into an mBuild compound object. Using this compound object, GIXStapose passes the points and the periodic boundary into Fresnel to build a scene and into diffractometer to calculate our diffraction pattern. A little bit of modification to the diffractometer code was necessary to expose the rotation matrix, and a little bit of logic was added to convert between the camera position in Fresnel and the rotation matrix in diffractometer. Then, Fresnel already had an interactive Qt widget, but I created one for diffractometer using PyQt and Matplotlib, and then tied these widgets together in a Qt application, the result of which is GIXStapose. Finally, let's go over an example of how GIXStapose could be used. Imagine you're a grad student. You've just run a molecular simulation of P3HT polymers for your advisor, and they've asked you to make a figure for the paper you're working on, and you've made the figure and you've calculated your diffraction pattern using a GUI, let's say GIXStapose, and your advisor comes back with feedback and they want a slightly different angle on your figure and they want you to use a different color. So it's back to the drawing board and you need to recreate this figure, but fortunately you used GIXStapose and you kept track of your camera information, and so recreating this figure from the exact point that you were at should be fairly straightforward. So in this example, we're going to import PySide2 Qt Core widget and use a Jupyter Notebook magic to let the Qt widget know that we'll be using it for the GUI. This will make an additional Python window pop up in your taskbar, so don't be alarmed. Next, we'll load up our output file into an mBuild compound and paste in our camera object that we saved. Create a scene using GIXStapose's create scene function from our mBuild compound. And here we're going to change our color by setting a color dictionary with CA set to gray. This color keyword can also take in any Matplotlib color map, and it uses Matplotlib's color definitions under the hood. Then we can open up an interactive scene view widget with this scene view and manipulate the scene using our mouse in the window that pops up. after we manipulate the scene, if we print out the camera again, we can see that it's changed from what it was originally. Then, if we're happy with our new scene, and we can render it using Fresnel's high-quality path tracer. And finally, we can save this to any image format using Python Image Library. We can do the same thing with calculating our diffraction pattern using the diffractometer class in GIXStapose, loading up our compound using the diffract from camera function to calculate the diffraction pattern from the exact camera that we used, and then finally saving our figure. We're eager to hear if GIXStapose is useful in your analysis and what features might make it more useful. Thank you so much for your time and attention.